Hello guys and welcome back to the electrical channel. Today we're going to talk about magnetism. We're going to touch some key points like the ampere turns, demagnetize, electromagnets, the electron, spin patterns, flux, flux density, left-hand rule, lines of flux, lodestones, magnetic domains, magnetic molecules, magnetomotive force or MMF, permeability, permanent magnets, reluctance, residual magnetism, and saturation. So I hope you can join me today so we can discuss all these exciting points in the following tutorial. Magnetism is one of the most important phenomena in the study of electricity. It is the force used to produce most of the electrical power in the world today. The force of magnetism has been known for over 2,000 years. It was first discovered by Greeks when they noticed that a certain type of stone was attracted to iron. This stone was first found in Magnesia in Asia Minor and was named magnetite. In the Dark Ages, strange powers of magnet were believed to be caused by the evil spirits or the devil itself. As you know, the Earth is a magnet. The first compass was invented when it was noticed that a piece of magnetite, a type of stone that is attracted to iron, placed on a piece of wood floating in the water, always line itself north and south. Natural magnets became known as leading stones or nodestones. The reason that the lodestone aligns itself north and south is because the Earth itself contains magnetic pole. As you know, we have geographical north and south and the actual magnetic north and south poles. The angular difference between the two is known as the angle of declination. Permanent magnets. Permanent magnets are magnets that do not require any power or force to maintain their field. They are an excellent example of one of the basic laws of magnetism, which states that energy is required to create a magnetic field, but no energy is required to maintain a magnetic field. Man-made permanent magnets are much stronger and can retain their magnetism longer than natural magnets. The electron theory of magnetism. There are actually only three substances that form natural magnets. Those are iron, nickel, and cobalt. Why these materials form magnets has been the subject of scientific investigations resulting in an explanation of magnetism based on the electron spin pattern. It is believed that electrons spin on their axis as they orbit around the nucleus of the atom. This spinning motion causes each electron to become a tiny permanent magnet. Although all electrons spin, they do not all spin in the same direction. In most atoms, electrons that spin in opposite directions tend to form pairs. Since the electrons pairs spin in opposite directions, their magnetic effects cancel each other out. As far as having any effect on distant objects, the similar manner two horseshoe magnets connected together would be strongly attracted to each other, but will have little effect on the surrounding objects. An atom of iron contains 26 electrons. Of these 26, 22 are paired and spin in opposite directions, canceling each other's magnetic field. And the next to the most outermost shell, however, 4 electrons are not paired and they spin in the same direction. These 4 electrons account for the magnetic properties of iron. At a temperature of 1420 degrees Fahrenheit or 771 degrees Celsius. The electron spin patterns rearrange themselves and iron loses its magnetic properties. When the atoms of most materials combine to form molecules, they arrange themselves in a manner that produces a total of 8 valence electrons. The electrons form a spin pattern that cancels the magnetic field of the material. When the atoms of iron, nickel, or cobalt combine, however, the magnetic field is not canceled. The electrons combine so that they share valence electrons in such a way that their spin patterns are in the same direction, causing their magnetic fields to add instead of cancel. The additive effect forms regions in the molecular structure of the metal called magnetic domains or magnetic molecules. These magnetic domains act like permanent magnets. A piece of non-magnetized metal has each molecule of a magnetic material itself is a small magnet. If a permanent magnet were to be cut into pieces, each piece will become a tiny separate magnet. Magnetic materials. Magnetic materials can be divided into 3 basic classifications, and these are ferromagnetic. It means that materials are metals that are easily magnetized. Examples of these materials are iron, nickel, cobalt, and manganese. Paramagnetic. This means that materials are metals that can be magnetized but not as easily. Third is diamagnetic. These materials are either metal or non-metallic materials that cannot be magnetized. The magnetic lines of force tend to go Some of the best materials for the production of permanent magnets are alloys. One of the best permanent magnet materials is alnico 5, which is made from a combination of aluminum, nickel, cobalt, copper, and iron. Another type of permanent magnet material is made from a combination of barium ferrite and strontium ferrite. Ferrites can have an advantage in some situations because they are insulators and not conductors. They have a resistance of approximately a million ohms per centimeter. These two materials can be powdered. The powder is heated to a melting point and then rolled and heat treated. This treatment changes the grain structure and magnetic properties of the material. The new type of material has a property more like stone than metal and is known as a ceramic magnet. Ceramic magnets can be powdered and mixed with rubber, plastic, or liquids. Ceramic magnets materials mixed with liquids can be used to make magnetic ink, which is used on checks. Another frequently used magnetic material is iron oxide. Magnetic lines of force are called flux. The symbol used to represent flux is the Greek letter phi. Flux lines pattern similar to the one we see in the Earth model. Basically, the lines of flux, magnetic lines of flux repel each other and never cross. All the magnetic lines of flux do not flow. It is assumed they are in a direction from electromagnetics. A basic law of physics states that whenever an electric current flows through a conductor, a magnetic field is formed around the conductor. Electromagnets depend on electric current flow to produce a magnetic field. They are generally designed to produce a magnetic field only as long as the current is flowing. They do not retain their magnetism when the current flow stops. Electromagnets operate on the principle that current flowing through a conductor produces the magnetic lines of flux act to produce a stronger magnetic field. A coil with 10 turns of wire will produce a magnetic field that is 10 times as strong as the magnetic field around a single conductor. Another factor that affects the strength of the electromagnetic field is the amount of current flowing through the wire. An increase in current flow will cause an increase in the magnetic field strength. These two factors that determine the number of flux lines produced by an electromagnet are the number of turns ratio. Ampere turns are determined by multiplying the number of turns of wire by the current flow. Core materials. Coils can be wound around any type of material to form an electromagnet. The base material is called the core material. When a coil is wound around a non-magnetic material such as wood or plastic, it is known as an air core magnet. When a coil is wound around a magnetic material such as iron, soft steel, or something similar, it is known as an iron core magnet. The addition of the magnetic materials to the center of the coil can greatly increase the strength of the magnet. If the core materials cause the magnetic field to become 50 times stronger, the core material has a permeability of 50. Permeability is a measure of a material's willingness to become magnetized. The number of flux lines produced is proportional to the ampere turns. The magnetic core material provides an easy path for the flow of magnetic lines in much the same way a conductor provides an easy path for the flow of electrons. This increased permeability permits the flux lines to be concentrated in a smaller area, which increases the number of flux lines per square inch or per square centimeter. In a similar manner, a person using a garden hose with an adjustable nozzle attached to it can adjust the nozzle to spray. Another common magnetic measurement is reluctance. Reluctance is the resistance to magnetism. In materials such as soft iron or steel has a high permeability and low reluctance. If the current flow in an electromagnet is continually increased, the magnet will eventually reach a point where its strength will increase. Saturation occurs when all the molecules of the magnetic material are lined up. Saturation is similar to pouring a 5-gallon of water into a 5-gallon bucket. Once the bucket is full, it simply cannot hold any more water. If it became necessary to construct a stronger magnet, a larger piece of core material will be required. When the current flow through the coil of a magnet is stopped, there might be some magnetism left in the core material. The amount of magnetism left in the material after the magnetizing force has stopped is called residual magnetism. If the residual magnetism of a piece of core material is hard to remove, the material has a high coercive force. Coercive force is a measure of a material ability to retain magnetism. A high coercive force is desirable in materials that are intended to be used as a permanent. Coercive force is measured by determining the amount of current flow through the coil in the direction opposite to that required to remove the residual. Magnetic measurement. The terms used to measure the strength of the magnetic field are determined by the system that is being used. There are 3 different systems used to measure magnetism: the English system, the CGS system, and the MKS system. Let's get to the English system first. In the English system of measured magnetic fields, the strength is measured in a term called flux density. Flux density is measured in lines per square inch. the Greek letter phi. Also in the English system, the term is used to describe the total force producing a magnetic field or flux. The CGS system. In the CGS system, centimeter gram second system of measurement, one magnetic line of force is known as Maxwell. A Gauss represents the magnetic force of 1 Maxwell per square centimeter. In the English system, magnetomotive force is measured in ampere turns. In the CGS system, Gilberts are used to represent the same measurement. Since the main difference between a conversion factor can be used to help convert one set of units to the other. The MKS. In this system, the main unit of magnetic measurement is the dyne. D-Y-N-E. The dyne is a very weak amount of force. One dyne is equal to 1/27,000 of an ounce, or it requires 27,800 dynes to equal a force of 1. Magnetic polarity. The polarity of an electromagnet can be determined using the left-hand rule. When the fingers of the left hand are placed, if the direction of current flow is reversed, the polarity of the magnetic field will also be reversed. Demagnetizing. When an object is to be demagnetized, its molecules must be disarranged as they are in a non-magnetized material. This can be done by placing the object in the field of a strong electromagnet connected to an alternating current AC line. Since the magnet is connected to AC current, the polarity of the magnetic field reverses each time the current changes direction. Molecules of the object to be demagnetized are, therefore, aligned first in one direction and then in the other. If the object is pulled away from the AC magnetic field, the effect of the field becomes weaker as the object is moved away. The weakening of the magnetic field causes the molecules of the object to be left in a state of disarray. The ease or difficulty with which an object can be demagnetized depends on the strength of the AC magnetic field and the coercive force of the object. An object can be demagnetized in two other ways. If a magnetized object is struck, the vibration will often cause the molecules to rearrange themselves in a disorderly fashion. It may be necessary to strike the object. A list of devices that operate on magnetism will be very long indeed. Some of the more common devices are electromagnets, As a matter of fact, the speaker is the most common device that operates on the principle of magnetism. The speaker produces sound by moving a cone. The movement causes a displacement of air. The tone is determined by how fast the cone vibrates. Low or bass sounds are produced by vibrations in the range of 20 cycles per second. High sounds are produced when the speaker vibrates in the range of 20,000 cycles per second. The speaker uses two separate magnets. One is a permanent magnet and the other is an electromagnet. The permanent magnet itself is stationary and the electromagnet is attached to a speaker cone. When current flows through the coil of the electromagnet, a magnetic field is produced. The polarity of the field is determined by the direction of current flow. The electromagnet has a north polarity. It is repelled away from the permanent magnet, causing the speaker cone to move outward and displace air. When the current flow reverses through the coil, the electromagnet has a south polarity and is attracted to the permanent magnet. The speaker cone then moves inward and again displaces air. The number of times per second that the current flow the coil reverses determines the tone of the speaker. Thank you guys for joining me again